Hey students, on this clip we're going to be going over 4 examples on how to calculate, on how to determine if a function is continuous using the continuity test. Alright, so to get started, let's take a look at, review the continuity tests. So let's write this down, continuity tests. Now there's 3 criteria that are necessary to determine continuity. And we went over this in part 1 of the tutorial, but let's just go over it again just to make sure we have it fresh in our minds. So um, f of x is continuous at x equals c if the following conditions are satisfied. Number 1, f of c exists. Basically, c has to be in the domain of the function and has to have a specific output. Secondly, the limit has to exist. So the limit is x approaches c of the function has to exist. And then last but not the least, the value of the limit has to match the value of the function. So the limit as x approaches c of the function has to be equal to the value of the function at the value that x is approaching. So it has to be equal to f of c. Alright, so these 3 conditions must be satisfied in order for one to be able to conclude that a function is continuous at a specific point, okay? Alright, let's go ahead and take a look at example number 1. We have the piecewise defined function f of x equals the absolute value of x minus 4 when x is less than 4. It's equal to 3 when x is equal to 4 and is equal to x minus 4 over the square root of x minus 2 when x is greater than 4. And the a value that we're looking at for this problem is for a equals 4. Okay? Alright, so let's start with let's start with test number 1. Does f of a exist? That's a question we need to answer first. So we know that a is 4. So in this function, f of 4 is equal to 3. So it exists. So it passes test number 1. Let's take a look at test number 2, which has to do with limits. Does the limit exist? Since we have 2 different functions going on here, let's identify what our functions are. To order them accurately, I like to make a number line. The partition or the a value where the switch happens is 4. So to the left, when you're approaching 4 from the left, the function that's in play is the absolute value of x minus 4, because this region is less than 4. And then when you're approaching 4 from the right, the function in play is x minus 4 over, we're at x minus 2. Okay, so we need to do the left and right hand limits since we have 2 different functions in both directions. So let's start with the left hand. All right, our left side. All right, so the left-handed limit, we're going to compute the limit as x approaches 4 from the left of the absolute value of x minus 4. Okay, so this becomes a limit as x approaches 4 from the left of plus or minus x minus 4. Now, since we're approaching 4 from the left, this limit is going to have the negative, this absolute value quantity is going to have a negative sign. Okay, so this is equal to the limit as x approaches 4 from the left of negative x minus 4. Okay, now let's go ahead and make the substitution. So this is going to become negative 4 from the left minus 4, which is equal to negative 0 from the left. Since 0 has an orientation, our final answer is 0. So that's the left-handed limit. Okay, now let's shift our attention to the right side, to the right-handed limit. From the right hand, All right, so what is the limit as x approaches 4 from the right? The limit as x approaches 4 from the right, the function in play here is x minus 4 over the square root of x minus 2. Okay? If we plug in 4, let's see what happens. I'm going to put this in green because we're going to be having some complications. If we plug in 4, we're going to have 4 from the right minus 4 over the square root of 4 from the right minus 2, which equals 0 from the right on top over, this is going to be 2 from the right minus 2, which equals to 0 over 0, right? That's what it looks like basically. So if you divide these two, you're going to have, it's going to be undefined, all right? So we can figure out the answer this way. So what you have to do is go back to the original function and see if we can simplify this and determine if the discontinuity is removable. And if it is, we can just factor it out and remove it, okay? So let's go back and evaluate this limit differently. So limit as x approaches 4 from the left, from the right, of x minus 4 divided by the square root of x minus 2. So what I'll do is I'm going to rationalize the denominator. Okay, so multiply by the square root of x plus 2 on the top and bottom, square root of x plus 2. Okay, and then when we work this out, this is going to become the limit as x approaches 4 from the right of x minus 4 times square root of x plus 2, and that whole story divided by, let's see, see what's going on here. So we'll divide that by, if you distribute this is a difference of squares, so it's simply going to be x minus 4, okay? X minus 4. All right, so what happens is that this x minus 1, that one divide out, and your limit now becomes the limit as x approaches 4 from the right of the square root of x plus 2. And then if you plug in 4, you're going to have the square root of 4 square root of 4 from the right plus 2, which equals 2 plus 2, and final answer is 4. Okay, so what can we say about the limit as x approaches 4 of f of x? Well, you notice that the left and the right hand limits are different, so the limit does not exist. Okay, so it basically fails test 2. This fails test 2, since the limit as x approaches 4 of f of x does not exist. And this is because the limit as x approaches 4 from the left of the function is equal to 0, and that is not equal to the limit as x approaches 4 from the right, which we found out to be 4. So the left and right hand limits are different. Conclusion, the limit does not exist. Fails test number 2. And then the final conclusion of the whole problem is that f of x is not continuous. Okay? It's not continuous at x equals 4. And the type of discontinuity here, if you look at it, both of the left and right hand limits both approach finite values. The left hand limit approached 0, and then the right hand limit approached 4. So since they're both finite values, we have a jump discontinuity. Okay, we have a jump discontinuity. Okay. All right. Now let's take a look at question number 2. So for number 2, what if we had the function, piecewise defined function f of x equals 2x squared minus 3x minus 9 over x minus 3 when x is not equal to 3 and the function has a value of 9 when x equals 3. Okay, so what if we have this function and the a value is equal to 3? Alright, so let's go ahead and determine if this function is continuous using the continuity test. Part number 1I is we'll have to show that f of a exists. So is that the case? Does f of a exists? Alright, so f of a is basically f of 3. So what's the output when you input 3 into this function? When x is at the value of 3, the output value is 9. So f of 3 equals 9. That shows that f of a does exist. So this function passes test number 1. Alright, let's subject it to test number 2. The limit has to exist. So the question is, does the limit as x approaches 3 of f of x exist? Does it? Well, let's see. So we're going to compute the limit as x approaches 3 of 2x squared minus 3x minus 9, because when you're approaching 3, you're not at 3, right? So this is a function that's in play when you're not at the value of 3. Okay, so from the left and right, this is the function we're going to consider. Plugging in 3, you can clearly see that we'll have some complications in the denominator, so we have to see if we can reduce this discontinuity here. So let's extract the numerator, 2x squared minus 3x minus 9. And I'm going to go ahead and factor this by grouping. So AC goes on top. AC negative 18. B is negative 3. We can use 6 times 3 is 18. So 6 and 3. The bigger one is negative since the sum is a negative. Okay? Alright, so let's factor this. We have 2x squared minus 6x plus 3x minus 9. And then we break it down to center and factor by grouping. From the first two, I'll take out 2x. And I'm left with x minus 3. And then from the last two, I'll take out 3. And you're left with x minus 3. So the factored form is x minus 3 times 2x plus 3. Okay, let's insert it back in the numerator here. So this limit becomes a limit as x approaches 3 of x minus 3 times 2x plus 3. And that expression divided by x minus 3. Okay? Now what you can see is that this discontinuity here is removable. So let's go ahead and remove it, cancel it out. Now we can now plug in, or let's rewrite it. This limit now becomes the limit as x approaches 3 of 2x plus 3. Okay? Now plug in 3, we have 2 times 3 plus 3. 6 plus 3 is 9. Okay? So the limit does exist, which is excellent. So the limit exists. It passed test 2. Now the final test is test number 3. Does the limit as x approaches a of the function equal to the value of the function? Is that the case? And the answer is absolutely. We were just able to establish that the limit in part 2 as x approaches 3 of the function is equal to 9, and that is equal to f of 3. Okay, so it passes test 3. Alright, so since f of x passes tests 1 to 3, the function is what? The function is continuous at x equals a, which is 3. Okay? So there you have it. All right, let's take a look at question number 3. Now, what if we have the following situation? We have, we're to calculate number 3, we had the piecewise defined function f of x equals 3x plus 5 when x is less than 3, and it has a function, the function 2x plus 9 over 2 when x is greater than or equal to 3. Okay? And for this problem, the value a is equal to 3. So let's see, well, let's determine if this function is continuous at this specified a value. All right, test I. Does f of a exist? That's the first test. Does f of a exist? At x equals a, which is 3, this is a function that's in play because of this inclusive mark right here for x. So when x equals 3, this is a function. So f of 3 is equal to 2 times 3 plus 9 over 2. Okay? So we have 6 plus 9 over 2. Put this over 1. We can express this as 12 over 2. So 12 over 2 plus 9 over 2 equals 21 over 2. So f of a exists. All right, so the function passes test number 1. So let's take a look at test 2. Test 2, the question is, does the limit exist? Does the limit as x approach a of the function exist? All right, so we have we have to check the left and the right hand limit. So let's start off with the left hand limit. Well, let's order the functions first of all so we know exactly what's going on where. So the a value that we're looking at is 3. To the left, less than, the function in place 3x plus 5. And then to the right, we have 2x plus 9 over 2. Okay, so let's do the left hand first. Left hand. For the left-handed limit, we're going to compute the limit as x approaches 3 from the left, and the function in place 3x plus 5. And that equals 3 times 3 plus 5. And you have 9 plus 5, which is 14. Okay, now the right hand limit. For that one, we're going to calculate the limit as x approaches 3 from the right of 2x plus 9 over 2. Okay, we'll plug in 3. It's just the same thing as what we did up here. 2 times 3 plus 9 over 2. Final answer was 21 over 2. We skipped the steps, 21 over 2. So what does this tell us? Since the left and the right hand limits are different, the limit does not exist. Okay, so the limit as x approaches 3 of f of x does not exist. Since the limit as x approaches 3 from the left of the function is not equal to the limit as x approaches 3 from the right of the function. Okay, so this function basically fails test 2. It fails test 2. All right, so the type of discontinuity we have here, since they both approach finite values that are different, we have a jump discontinuity. Jump discontinuity. All right, so there you have it. All right, let's take a look at question number 4. Question 4, we have the piecewise defined function f of x equals 1 minus cosine x over x when x is less than 0 is equal to 0 when x is equal to 0, and it is sine x when x is greater than 0. Okay, so let's say we have this piecewise defined function, and we are to determine if it's continuous at a equals 0. All right, let's go ahead and do the 3 tests. Test number 1. Does f of a exist? F of a exists? That's the question. Let's see. F of A is basically f of 0, since A is equal to 0. And when we input 0 into this function, our output is clearly 0. So f of A exists, so it passes test 1. How about test 2? Does the limit as x approaches A of f of x exist? Does the limit exist? Okay, to determine this, we're going to do the left and the right hand limits. We have two functions, so that's necessary. Let's use a number line to organize our functions on the left and right hand side. The sign change happens at 0. So when you're approaching 0 from the left, you're looking at 1 minus cosine x over x. And then when you're approaching 0 from the right, you're looking at sine x. Okay? Alright, so let's see. Does the limit exist? Let's start with the left-handed limit first. So, what is the limit as x approaches 0 from the left of 1 minus cosine x over x? Using the sandwich theorem, we know that this is 1, basically. Okay? But let's go ahead and show it. Oh, I'm sorry, I meant to say this limit is actually 0. Okay? So it's just one of the special limits you want to remember, that the limit of 1 minus cosine x over x is equal to 0. And that's a consequence of the squeeze theorem. Okay? So from the squeeze theorem, we know that the limit as x approaches 0 of sine x over x is 1. You want to remember that, and also an extension of that is the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. Okay? Alright, so let's show that this is the case. Let me show that to you real quick using identities. Let's evaluate this limit. If you plug in 0, you can clearly see that we'll have a 0 in the denominator, which makes the expression undefined. So we're going to rationalize the numerator by multiplying by 1 plus cosine x and 1 plus cosine x. Alright? When we multiply this out, this is going to become the limit as x approaches 0 from the left of 1 minus cosine square x over x times 1 plus cosine x. Okay? Now, using the Pythagorean identity, we can rewrite the numerator, when as x approaches 0 from the left, as sine square x, because we know sine square x plus cosine square x equals 1, hence 1 minus cosine square x is equal to sine square x. Alright, so that divided by x times 1 plus cosine x. Alright, so let's rewrite this limit in such a way that we can apply the squeeze theorem. So this we can write as the limit as x approaches 0 from the left of sine x over x times sine x over 1 plus cosine x. Okay? Using the squeeze theorem, we can establish that this limit is 1. And then this limit is going to be times sine 0. We can just substitute here because we don't have any complications, over 1 plus cosine 0. So this is going to become 1 times sine 0 is 0 over 1, because 1 plus, let me show you the work, 1 plus 1. Cosine 0 is 1, 1 plus 1, so this is just simply 1 times 0, which is equal to 0. Okay, so the left-hand limit of this function is 0 as x approaches 0. All right, let's go ahead and determine the right-hand limit and see if the limit exists or not. Right hand. So the right-handed limit is the limit as x approaches 0 from the right of sine x. Okay, and we can just do this by simply substitution. So sine of 0 from the right. What is sine of 0? If you draw your sine function, remember what your sine function looks like. It starts from the origin, and then it oscillates between 1 and negative 1. So it looks something like that. So sine of 0, you can clearly see 0. So sine of 0 is 0. All right, so what's the conclusion here? The limit definitely exists, right? In this problem, the limit as x approaches 0 of f of x exists since the limit as x approaches 0 from the left of the function is equal to 0, and that is exactly what the right-handed limit is, the limit as x approaches 0 from the right. Okay? So it passes the limits test, test number 2. All right, let's subject it to test number 3. And the question is, the limit as x approaches 0 of the function is equal to the value of the function at the specified a value, which is 0. Is this the case? Well, the answer is yes, because the limit as x approaches 0 of the function was equal to 0, right? We just determined that, and that is also equal to the value of the function at 0. So it passes test number 3. Okay? So since it passes all 3 tests, we can conclude that the function f of x is continuous at x equals the a value, which is 0. Okay, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel. You can post a comment to let me know what you think about this clip. You can like it or share it via your respective social networking program, Facebook, Twitter, or LinkedIn. More videos can be found on microsoft.com/calculus, or you can just scan this QR code for direct access. Thanks again for watching and have a wonderful day.